This is also why I ask you guys all, turn your camera on, unless you really need to, go somewhere. So today we are going to talk about the redox reactions. Basically, this is for question number 7 to 12 in the National Part 1, and question number 5 and number 6, or number 6 for reaction writing in the National Part 2. I hope this can also give you some sense or better background for you to prepare the other topics. First, would you mind to take, let's say, 2 minutes to finish, all of those reactions? You just, finish those, what do you know, and leave those, you don't know. Okay. And I will also write down my answer here. You can check with me at any time, and then we'll have, a quick discussion. So you don't need to balance the reactions, since in the part 2 for question number 5 and number 6, you are also not required to balance the reactions. So probably it would be better if you have the printed version and you can take notes. Otherwise, you probably need to copy some stuff, right, in order to have a decent notes. So you will feel some difficulty in working on this, since this is probably the first time for you to learn a lot of reactions. So I hope after the class today, by the end of this session, you have a much better understanding, regarding analyzing a new redox reaction. So what I'm going to talk about here is not only to teach you the reactions, the contents, but also to give you a strategy. It seems like most of you are good. Is there anyone who needs a little bit more time before we start the group discussion? Okay, cool. So, all of the reactions I put here are very selective because there are so many reactions, right? There must be a reason why I pick up those few. The first reaction, combustion must be redox. And I put 2 metals and 2 non-metals here. Just want to show you oxygen gas is a very strong oxidizing agent. It can react pretty much all of the elements, right? Including a lot of compounds. So lithium as an alkaline metal it will produce just the regular oxide. But sodium, if you burn the sodium in the oxygen gas or even in the air, you will get a very pale yellow product, which is not sodium oxide, it is sodium peroxide. So this is the special property for some of the alkaline metals, such as sodium, potassium, including the others, rubidium, cesium. They are very likely to form complicated oxides, including peroxide or even superoxide, right? You probably know the superoxide, right? Peroxide is like O2 2 minus. This is per oxide. So the per means it has a slightly higher oxidation number. And we also have the O2 1 minus. This is called superoxide. How to spell superoxide? Is this correct? Yes? I think so, right? So this one is a little bit special, right? Phosphorus, sulfur, they are both nonmetals. Phosphorus will, change into the oxide with the highest oxidation number. So what is the highest oxidation number for phosphorus? You need to check the group number, right? Phosphorus is in 5A group. So plus 5 is the highest for it. Make sense? So we got P4 O10. In some textbook, it is also written as P2 O5, but actually is a molecular compound. So you don't have to write down into the empiric formula. If you are interested, I can briefly show you, what is the structure of the P4 O10. So the 4 phosphorus are in a tetrahedral relationship, and each of the 2 are connected by a single bonded oxygen, for example, like this. And also here, and also here, and also here. So as you can see, there are 6 oxygens used already, right? And right now, each phosphorus is plus 3 because it, I think I probably had too many for one of them. Which one? This one. I'm sorry. Yeah, so now each phosphorus have 3 bonds. So each phosphorus is plus 3 in oxidation number. So each of them will have a double bonded O. It's like this, the structure like this. Obviously, you can draw it in a better way, in a more beautiful way. Just in case you are interested in the structure of the P4 O10. Sulfur actually is in 6A group. So theoretically, it should produce SO3, right? Based on the similar idea. But actually, SO2 is more thermodynamically stable. So in industry, when we need to produce sulfuric acid, which we are going to discuss later. So the first step is to convert the sulfur into SO2 and then further into SO3. But this step is much harder. The oxidizing agent is still O2, but this step is much harder. So the major products when sulfur is burned in air or in oxygen gas is SO2. So this is also one of the sources of the acid rain, right? When we burn the coal, the sulfur in the coal will change into SO2 and further change into sulfurous acid and maybe sulfuric acid later, right? Which will acidify the rainwater, make the pH lower than around 5.8. Because 5.8 is the pH for the regular acid rain, for the regular rainwater due to the existence of carbon dioxide or carbonic acid. Make sense to you? Okay, good. So do you have any question regarding the first type of redox, combustion?
For combustion, how do you tell whether it's going to be like peroxide or superoxide if it's not lithium and normal oxygen?
This is more likely based on experience, or you can have some summary. Basically, if the metal is very reactive, such as alkaline metal or those bottom elements in the second group, alkaline earth metal, they are very likely to form peroxide or even superoxide, and they might get a mixture. But lithium or magnesium, those kind of relative non-reactive alkali or alkaline earth metal, they can form the regular oxides. I was told by a guy, Suraj, a guy from your school, so they got a question in the science book, maybe last year. So science book, I don't know how many of you play science book before.
I'm on the science bowl team. Yeah.
Cool. So it's a kind of very fast-paced, quiz book, right? You don't have time to really think too much. You need to be very fast. So one of the questions is asking, what is maybe the name or the formula when sodium is burned in oxygen gas. So the guy from the South School, he quickly applied sodium oxide, and then he quickly realized it's wrong because he didn't know it should be sodium peroxide. But it just in that case you don't have time to really work on your answers. Okay, the next part is also combustion, but it's not in air. It's with some oxidants, right? For example, nitrogen gas, carbon dioxide, chlorine gas, and even sulfur. Sulfur, probably this reaction is not called combustion because you probably cannot see the flame, right? When we define something as combustion, we need to see the light, the burning, the flame, right? And need to release a lot of heat. So it's pretty rigorous. Although when you mix these two, if you grind them, the reaction is also pretty rigorous, but you cannot see any flame. But I just put it here. So the first example here, what I want to say is magnesium is one of the few exceptions. Metals can react in nitrogen gas because we know nitrogen gas typically is an inert gas, right? So used to, as a protecting gas. But here, if you have magnesium, nitrogen gas can be the oxidizing agent. It will produce magnesium nitride. I think based on the group of each element, you are supposed to figure out what is the formula, right? It's easy to make mistake into something like this, right? Makes sense. Magnesium can also, combust in carbon dioxide. If you analyze from the redox perspective, magnesium is the reducing agent, right? Carbon dioxide is the oxidizing agent. And I think you guys can search in the YouTube. Now you don't need even to search. You can just check the link. You click the link in the PDF. It will guide you to a YouTube video, and you can watch the video by yourself. You will see some black solid appeared in the container. That is carbon. That is the carbon. So carbon is the product. So somehow it makes sense, right? Now say if you don't know this reaction, you are asked to analyze this reaction. I think you can also have some strategy. Magnesium as a metal, it must be oxidized, right? So the product definitely has to be magnesium oxide. So you only need to think about which element oxidizes magnesium. So here, the -2 oxide definitely cannot do it because -2 is already the lowest for oxygen. So it has to be the +4. So the only thing probably you're not very sure is the product is carbon or carbon monoxide, right? Probably this is the only thing you're not very sure. Next one is a comparison. Iron as a transition metal with multiple oxidation numbers. When it met with a very strong oxidizing agent, it produced the products with the highest oxidation number, +3. When it met with a mild or weak oxidizing agent, it can change into the +2 products. So this is why the product is like this. This is iron 3 chloride. This is iron 2 sulfide. Can you guys have a quick comparison between these two? How can we conclude chlorine is a stronger oxidizing agent than sulfur? Electropotential. You definitely can use the standard reduction potential, but without referring to the data. Is there any way? Electron activity. I think this can be a good perspective, but we can directly explain, from the atomic structure, because we know chlorine and sulfur, they are in the same period, right? And chlorine has one more proton, which means it's more eager to gain electrons. And gaining electrons actually shows how strong the oxidizing agent is, right? Because as an oxidizing agent, it needs to be reduced. And actually this process gains the electrons. So make sense? So similarly, I think you definitely can compare O2 and S, which one is a stronger oxidizing agent. So no doubt it's O2, right? Because O2 has a smaller size. They are in the same group, but O2 is on the top, right? Okay. So next type, any question here? Combustion with other oxidant? Good. The next part is the single displacement, or you can call it single replacement, the metal single displacement. So here I give a few examples. Iron, as an example, pre-hydrogen metals, pre-hydrogen metal, post-hydrogen metal, we are going to discuss the concepts later. So when it reacts with the acid, it will change into iron 2+ and hydrogen gas. And if it's copper, if it is a post-hydrogen metal, it cannot react with the regular strong acid. There's no reaction. Copper is more reactive than silver, so that is why there is a single displacement in this direction. So if you put silver into the copper 2+, there will be no reaction. Makes sense, right? And similarly, non-metals can also have the single displacement based on their reactivity. So the most typical example is the single displacement of the halogen halide. So one of the halogen reacting with another halide. For example, if you bubble the chlorine gas into the Br- solution, since chlorine, if we compare with bromine, which one is a stronger oxidizing agent? No doubt it should be chlorine, right? So similarly, if you compare Cl- and Br-, which one is a stronger reducing agent? When we say a stronger reducing agent, we are talking about which one is easier to lose electrons, right?
Br-.
Definitely Br-, because it has a larger size, right? So it's easy to lose electrons. So this is why this reaction is spontaneous. You can watch the video by yourself here, the halogen halide displacement, because this reaction will have a color change because Br2 is reddish brown, right? I think you definitely need to know Br2 is reddish brown. Chlorine gas is a kind of greenish yellow or pale yellow. And iodine, which is the darkest, is purple, right? Purple both in solid and also in solution. The next one probably is an unknown reaction, but I think you can also try to analyze fluorine gas as the strongest oxidizing agent with a standard reduction potential of more than 3.0 volts, right? So this one definitely want to gain electrons, change into fluoride. And the fluoride must be, bound with the H. So one of the products definitely is HF. And then we must oxidize an element, right? So it should be the -2 oxygen. So this is why O2 is produced. Make sense? So this is also a single displacement. Although it's a little bit tricky, but actually if you analyze the redox principle behind this, actually it's reasonable. The last type actually are the most typical in AP Chem, right? Redox titrations by using permanganate and iodine. So here I put two examples of permanganate. They are both, in the AP chemistry in the experiments. The first one is to oxidize oxalate. I want to briefly talk about, why oxalate is so easier to be oxidized. As we know, if it's another carboxylic acid, it cannot be oxidized by the permanganate. There is no reaction. So which means carboxylic acid actually is pretty stable. But why the oxalate or the oxalic acid, which is also a carboxylic acid, can break this bond to produce carbon dioxide? If you analyze the structure, you realize this carbon carries the partial positive charge. This carbon also carries the partial positive charge. So which make this bond unstable because the two positive charge will collide with each other, destabilize the molecule. So this is why oxalic acid can be easily oxidized, turned into carbon dioxide. And another one, hydrogen peroxide, -1 oxygen, right? It can be oxidized into O2, So we don't need to balance it. So the net ionic equations are just like this. So now I think we probably can take some time to analyze the introductory question. Why do we need to summarize the reaction types? We definitely don't have time to finish learning all of the reactions, right? So this is why we do the classification, because we want to start from a few typical examples, and then we extend the similar idea or principle into the other unknown reactions, right? So if you see an unknown redox reaction, I hope you can always analyze which one is oxidized, which one is reduced. And then you probably will get some clue. Okay, any questions so far? Next, let's talk about the metal reactivity series. Here I put a full list. Obviously, don't need to remember the whole list, but I hope you can get a sense, especially to the most typical non-reactive metals. I call it post-hydrogen metals because in the standard reduction potential series, they are all positive, which means they are, how to say that? Their elements are harder to lose electrons. Their cations are easier to gain electrons compared to the hydrogen system. Make sense, right? So there are copper, mercury, silver, gold. Maybe you can add one more, is the platinum, right? Platinum. Okay, we also have a long list of the reactive metals, right? And what is the hydrogen? The hydrogen is here, so which means all of those elements actually are more reactive than hydrogen. But you will see those are mainly alkali and alkaline earth metals, right? They are the most reactive. And then some of them in the middle, most of them are the transition metals, right? Although there are a bunch of transition metals which are not so reactive, right? So you don't need to memorize the whole list, but you need to have a sense. So how to differentiate them? The first few, most reactive, they can displace hydrogen gas from water. So I think you can, have a quick check with those reactions. Okay, give you 1 minute to write down, the equation. Okay, the first one definitely is barium hydroxide. But if we write down the net ionic equation, it should be Ba2 plus hydroxide, since it is a strong base, right? And also we should have hydrogen gas. Because barium is oxidized, we must have a certain element to be reduced, right? If we analyze all of the elements, it must be hydrogen, right? So this reaction is quite similar to the sodium reaction with water. It's pretty rigorous, right? It produces a lot of heat, so the hydrogen gas produced may be burned, right? Maybe burn. The second one, they can only displace hydrogen gas from the steam. Basically, it's the hot water vapor, which means they are less reactive. They are not so easy, right? Our mechanism is kind of in the middle. It doesn't need to react with the steam. It can react with the boiled water. So basically, we heat the boiling water. So we also got the magnesium hydroxide. In this case, the amount of the magnesium hydroxide is very, very minimal. You even cannot see the precipitate. And actually, you even cannot see any bubbles. You cannot see any bubbles. But how do we know the reaction actually is ongoing? We add some indicator, we add some phenolphthalein, and then we see the color of the solution change into pink during the boiling process. This is an evidence to support, actually there is a reaction, but the idea is pretty much the same. So I think here it's pretty much the same, but probably in this case, I will say the product is more reasonable to be zinc oxide, since it reacts with the water steam, right? Since zinc hydroxide is also easy to decompose, so it changes into the hydrogen gas as well. And for those not so reactive, they can only displace hydrogen from acid. So I think this is more straightforward here. And for those post-hydrogen metals, they cannot react with H+. So I have a few, extended questions here. Let's have a very quick look. So I think we already answered this question, because those metals, they have a more negative standard reduction potential than the SHE, standard hydrogen electrode. This one is 0 volts. And all of the pre-hydrogen metals, they are negative, right? Makes sense to you? And obviously the post-hydrogen metals have a positive, right? The second one, this is pretty straightforward. Zinc reaction with copper. Feel free, to take some time to watch the video, because the reaction is pretty, right? You will see the blue color of the solution is gone, and then a lot of solid, maybe red or maybe black, will be appeared on the surface of the zinc. Oh, sorry. This is just silver. Question C is pretty interesting. How do you think of the reactivity of the alkaline elements in the first group, down the group, and the second period elements across the period, and also the group 1B elements? What's your idea? Let's start from lithium, sodium, potassium, rubidium, and cesium. Down the group, they are getting more reactive or less reactive? Definitely more reactive, right? Size is getting larger, easy to lose electrons. Because when those metals reacting with water, it's the metal lose the electron and transfer to the water. And the H+ in the water gain the electron, right? Produce hydrogen gas. This is the idea. So definitely it's getting more reactive. How about here? Sodium, magnesium, aluminum, across the period is getting less reactive, right? Because there are more protons in the nucleus holding the electrons tighter, right? What is the evidence? the reaction with water. Sodium, put in water, very rigorous, right? Magnesium can only react with boiling water. Aluminum can only react with water steam, right? Oh, by the way, here, if you search in YouTube, you can easily find the video, right? Down the group, those alkali metals will react with water in a more rigorous way. Cesium, if you put in water, it will not only burning, it will explode, right? It will explode because it produces too much heat. How about this group? They are all used as money in the history, right? Copper, silver, gold. But it seems like they are down the group is getting more expensive, right? I think this is also evidence it's getting more non-reactive, right? Non-reactive. Okay. This is a very good question. I want you guys to to take a look at the two standard reduction potential here and have your analysis. You probably know the product is this, but why is not iron 3+? Maybe a good direction. Oh, I got an answer. The Fe2+, lower reduction potential means higher oxidation potential. Okay, I understand that. So if you analyze this two, maybe we can further calculate this. We can calculate this. Can you guys do a very quick, calculation? I think this is also a good practice for the USNCO, right? The Fe3+ to iron. I got one answer, 0.03, negative 0.03 volts. You guys can check with this answer. Give me a thumbs up if you agree. Great, great. Thank you. So now, let's suppose this is the correct answer. If you didn't finish, you definitely can take more time after class. If we compare these two, can we get the conclusion? Which one will be more spontaneous to produce the Fe2+ or the Fe3+? Definitely is the Fe2+, right? Because it's more negative. And the standard hydrogen, electrode is the cathode, right? I think there is also another way for you to analyze the reaction. Basically, the ion changed from 0 to ion 2+ and further changed into ion 3+. So the oxidizing agent is H+. You can analyze this reaction is spontaneous, but actually the second reaction is not spontaneous, right? It's not spontaneous because this one is much harder to be oxidized. Oh, that is a good question. So how about this? Should I say proportionation or disproportionation? This is a proportionation. So the reverse reaction is the disproportionation. This is the disproportionation. I apologize. I don't need to balance it. Which one do you think is spontaneous? The top one or the bottom one? This is a good question. Let's just analyze one. Let's try the bottom one, okay? So from ion 3+ to 2+, this is the cathode because it's the reduction, right? And then this one is the anode. So we just to make sure the cathode has a higher standard reduction potential than the anode. And then this reaction is spontaneous, right? So is this true here? It is, right? It is. So the second reaction actually is spontaneous. The first one is not. So guys, search in YouTube by yourself after class. Basically, you can search, let's say iron 3 chloride mixed with iron, and you will see the color of the solution will change from yellow to very light green. Because light green is the color of the iron 2 plus, yellow is the color of the iron 3 plus. Oh, this is a very interesting question. How does the reactivity affect the extraction of metals from their ores? If a metal is more reactive, it's more likely to be extracted by using electrolysis or not. So basically, what's the relationship between the reactivity of a metal with the method used to extract the metal from the ore? Let me give you a general idea. So now say if you have sodium and you have gold, which one is more likely to use the electrolysis to extract the element?
Sodium.
Sodium. Why sodium, Emily?
Because since gold is less reactive, it's more likely to exist naturally in like a pure gold state, whereas since sodium's more reactive, it's more likely to exist as like different compounds.
I see. This is a very good point. And also, even if not gold, for example, like mercury, it might not naturally exist as element in the earth, but it may form let's say oxide. But those kind of oxide will be not very stable and very easy to decompose. And actually, this is also the fathers of chemistry back to the 18th century, how they discover the composition of air. I remember who is this name, Lavoisier, right? So he got some idea from the other scientist. He heat the mercury oxide, turn into mercury, and get the oxygen gas, and further investigate the properties of the oxygen gas. I really want to show you so it's from Beautiful Chemistry, the setup they used. Beautiful Chemistry. This is a very good website. If you don't know, I strongly recommend you to watch the videos here. It is made by a group of chemistry students from USTC, which is the University of Science and Technology of China. So let me see. I think we can go to history. So famous chemists. No, those are just some famous chemical instruments. I think it's this one, Lavoisier's apparatus for studying mercury oxidation in closed environment. Oh, this one is a reverse reaction. He put the mercury in the left glassware, the container, and then in the right side, we have oxygen, we have air in the in this container, and then you will see after the oxygen gas is bind with the mercury level in the right side will go up, right? And actually, he estimated, how much higher it gets up, and then we know what is the volume percent of the oxygen gas in the air. This is actually the beginning of the modern chemistry, right? So this is why Lavoisier is regarded as the father of chemistry. So this is back in 1789, right? More than 300, less than 300 years ago. Okay. So our conclusion is the more reactive metal has to be, or is more likely to be extracted from the metal by using electrolysis, because you cannot find another stronger reducing agent to get it. For example, if you want to get sodium, you might think about, how about I find another metal which is more reactive than sodium, and then to reduce sodium from its compound, for example, sodium chloride, right? We add another metal to change it into sodium and get another stuff, the metal chloride. But this is pretty much impossible because there's no such a metal which is more reactive than the sodium, right? So this is why, we use electrolysis to electrode, those very reactive metals such as sodium, potassium, aluminum, right? Check this question from the National 2016 Part 1, question 39. We can have a quick look. This link work? Interesting. Not working. Let me see whether I can. Oh, I can. So we can have a quick look. I remember, we discussed this question in the season 3. Where is it? Oh, here. Which of the following metals is most likely to be produced through electrolysis? Gold, mercury, iron, right? Definitely is mercury. Oh, sorry, definitely is aluminum, right? Mercury, you just need to decompose the oxide. Gold, you probably can pick up on the ground, right? If you live hundreds of years ago. Right now, it's very hard. You need to be very, lucky. Iron, what is the standard method in industry to get iron? We put the iron oxide mixed with carbon, mixed with coal, and then put it into a furnace and heat to a very high temperature. And the carbon will change into carbon monoxide. The carbon monoxide can reduce the iron oxide. So the reaction, if we write down here, is let's take iron 3 oxide as an example. It reacts with carbon monoxide, and on the temperature, it changes into iron and CO2. Does this reaction make sense to you? So basically, carbon, hydrogen gas, carbon monoxide are the 3 standard, reducing agent used in industry: carbon, hydrogen gas, carbon monoxide, because they are all the relative lower, oxidation states. The last question: can post-hydrogen metals like copper and gold react with acid? The answer is yes, right? Yeah, as Suraj suggested, gold can react with aqua regia, right? A mixture of the concentrated nitric acid and hydrochloric acid. But the mechanism is not as simple as here, because theoretically, the acid itself cannot oxidize copper and gold by using the H+, right? Because the H+ is not that strong. So this part is always confusing because it's totally missing in the curriculum in AP Chem. You don't need to talk about honors chem. So this part, let's have a quick summary. So if you have the pre-hydrogen metals, when they meet with strong acid, I listed 2 strong acids here, HCl and diluted sulfuric acid. Those 2 are the most typical examples of strong acid. They will just produce the hydrogen gas. Makes sense, right? If they meet with the post-hydrogen metals, there will be no reaction because the H+ is not strong enough to oxidize those metals. And then if they meet with oxidizing acid, there is a definition of oxidizing acid in the Wikipedia page. You guys can check it later. So basically, there's no hydrogen gas produced because the way we define the oxidizing acids, or the anion of the acid actually has the ability. The anion of the acid, for example, concentrated sulfuric acid, is this part to be reduced, the +6 sulfur to be reduced. So this is why it will produce you the SO2, a +4 sulfur. This one is a toxic gas with a pungent, oddness, It can also be used to bleach the, how to call this name? I don't know. It's kind of, a type of dye. Do you guys know how to pronounce this name? For chi sign? I'm not sure. We'll stop. It's red. Because Chinese name is called Pin Hong. So this is how I know it's pink. It's red. But it doesn't make any sense to me, based on this English name. Okay, so which means if you have copper, such this one, copper reacting with the concentrated sulfuric acid, it will give you the SO2 and also the copper 2+, right? So you probably ask why the concentrated one is so special. I don't know. The concentrated one is just weird. Is very different from the diluted, sulfuric acid. The diluted sulfuric acid, the sulfate itself has no ability to oxidize the metal. It's the H+. So I don't want to confuse you. When we say oxidizing acid, it doesn't mean those acids are not oxidizing. They are also oxidizing, but they use H+ to oxidize the metals. But when we say the oxidizing acid, we are talking about the anion parts. The anion parts. Another one is concentrated nitric acid. I think you probably all watched this video before. The penny reacting with the concentrated nitric acid. In case you didn't watch it before, let's just quickly show you maybe a few seconds. I don't know why I cannot, make it into full screen, but I think it's good enough for us to see the color change, the bubbles. You will see, the penny, slowly dissolved in the solution. There are a bunch of reddish brown, gas produced. The solution changed to green and then slowly changed to blue, right? So what is the reddish brown gas? It must be NO2, the reddish brown gas, right? And the reason why in the beginning the solution is green is because some NO2 is dissolved in the acid. So you have a mixture color of like yellow plus blue. Blue is the copper 2+, yellow is the dissolved NO2. So the mixed color of these two change into green. And then when the reaction is ongoing, more heat is released and the NO2 is slowly, escape from the system. And finally, you see the blue solution, right? Another interesting reaction, when the nitric acid is diluted, and then it will change into the colorless NO gas. But you probably ask, how concentrated is called concentrated, how diluted is called diluted. Typically, we use around 10 mole per liter as a boundary. If it's more concentrated than 10 mole, let's say around 15 or 18 molar, and then it's very typical concentrated acid. If it's just a few moles, let's say 3-5 molars, they are diluted. I think there are a few very interesting reactions in the old local exams. For example, here, let's have a quick look. Here, number 3. You guys can have a quick look. What is the answer? You definitely cannot choose A. It's not hydrogen gas, okay? Because the H+ here is not strong enough, right? It's not strong enough in any place to oxidize silver. So it is NO. And why we need to emphasize in the absence of the air? Because NO can be easily oxidized into NO2 in the air. So actually this question is pretty, precise in description. we need to have no air, no oxygen gas in the system, right? Okay. There's an extended question. What are the reactions of the oxidizing acid, such as concentrated sulfuric acid, with non-metals? Can we just use carbon as an example? You guys can take 1 minute to write down, the reaction. But you cannot write the net ionic because in the concentrated sulfuric acid, there's pretty much no water, right? It's 98% concentrated. And typically, we want to emphasize it's concentrated because it has a very special property compared to the diluted sulfuric acid. This is the unknown reaction. How you analyze? Concentrated sulfuric acid definitely is the oxidizing agent here, right? So it will oxidize the carbon. And when carbon is oxidized, you need to think about is either carbon monoxide or carbon dioxide. Carbon dioxide definitely is a more stable product. So this is why you have carbon dioxide here. And then which element is reduced is the sulfur, right? So it must be SO2. And then you will have water. So this is the general idea, how you analyze the reaction. If you have no question about this, I will show you another, local problem. I think it's question number 7. For this one, I would like to, put a poll and get your idea. Number 7. I'm asking number 7, right? It seems like all the answers I got are wrong so far. Or maybe I'm wrong. Okay, never mind. Never mind. My bad. Okay, good. I got 7 votes. Any more? Oh, 9 votes. Good. Oh, got 1D. So the answer definitely is C, right? Because even when nitric acid is diluted, it will still produce NO rather than hydrogen gas, okay? Because in this case, the nitrate, the NO3 minus, is a stronger oxidizing agent than the H+. So this is why during the competition, the nitrate, always wins the game. It cannot produce hydrogen gas. And HCl, sulfuric acid, when they are diluted, they are not oxidizing acid. So this is why the H+ will play the role, change into hydrogen gas. So now I think you probably understand why this question needs to emphasize a dilute solution. Because if sulfuric acid is concentrated, it can also produce the gas products other than hydrogen gas, such as SO2, right? HF actually is not a strong acid. So if the metal is not reactive enough, maybe there's no reaction. But if the metal is reactive enough, it's okay. Because for sodium and other similar elements, they can even react with water directly, right? So HF is an acid. It definitely will be more rigorous. Okay, good. I think now we can, quickly talk about, what is the principle of the aqua rigor. So you guys know the aqua rigor is the mixture of concentrated nitric acid and HCl and hydrochloric acid. So when these two acids reacting with gold, Au or other, post-hydrogen metals, they will produce something like this. Wait a second, let me check whether my chart is correct or not. I think it's wrong. The reaction is like this. So now you probably can analyze what is the function of each acid. Willen, do you have any idea? What is the function of each acid?
Nitric acid oxidizes metal, and hydrochloric acid forms a complex.
So what benefit to form the complex?
It will shift the equilibrium towards the right side.
Very good. So without the chloride, let's say we only have the nitric acid, we cannot have this reaction because the standard reduction potential of nitrate NO is smaller than the standard reduction potential of Au3 plus with Au. So which means nitric acid itself is not strong. It's not strong enough. But with the chloride, because the chloride can complex with the gold 3 plus, and then change into this complex, which you can say shift the equilibrium to the right side, or you can also say it will lower down the potential, right? Now it's not standard anymore because you have the chloride, right? So it decreases the concentration of the Au3 plus, which will decrease the reduction potential, and then the reaction can shift to the right side now. Okay, very good. Before we take a break, do you guys have any further question about the parts we just finished? Okay, great. We'll take a 5 minutes break. Let's restart at 9:13 Eastern time. Okay, see you guys later. Hello, everyone. Welcome back. So after we talking about those fundamental, types of redox reactions, and the very interesting metals reacting with acid, we are going to go through a lot of different reactions. So here I pick up 3 representative metals: sodium, aluminum, iron, because each of them represents a certain group of metals. Sodium is the representative of reactive metals. Aluminum is for amphoteric metal. Iron is for transition metal with multiple oxidation numbers. So I think after we finish talking about all of those reactions regarding those 3 representative metals, I hope you will have a better understanding about all of the reactions regarding metals. So I probably don't have too much time for you to write down all of the reactions. So you guys can have a very quick going over of those reactions, and I'm going to take some time to write down the reactions. If they are in aqueous solution, I will try to write down the net ionic. You guys can still, turn your camera on, right? I think it's pretty good to see you guys and know your, response and reactions. Thank you, Andrew. So I will talk about a few reactions first, and then you guys can let me know, which other reactions you would like to have a further discussion here. I will pick up this reaction first, since this one was, assessed in the national part 2 before. This reaction, if we write down the chemical equation, actually, I will, write down in this way. So this step actually is a non-redox reaction. How to interpret the reaction in this way? So it's a double displacement, or you can say it's a hydrolysis. So in the sodium peroxide, you have sodium plus, you have peroxide. In water, you have H plus and hydroxide. And then the cation will bind with the anion, the anion will bind with the cation. So this is why hydrogen peroxide is produced. But this reaction is similar to a kind of acid-base neutralization, right? Because this is the base, this is the acid. And typically, acid-base neutralization are exothermic. And you know, hydrogen peroxide is unstable when heat is released at high temperature. So the hydrogen peroxide further decomposes into water and oxygen gas. So this is how you get an overall reaction like this. It's very hard for you to maintain the hydrogen peroxide in the solution under, such a rigorous, background. So if you try to analyze the next reaction, it's also quite similar. The next one I want to say is question number 5 and 6. This is a good comparison. So when the carbon dioxide is in excess, which means when carbon dioxide binds with water, I think I need to add, I don't need to add water. When it binds with water, it changes into carbonic acid. And the acid in excess and the base is not enough. So which means this diprotic acid will only dissociate one H plus because that's more than enough, right? So it doesn't need to change into the carbonate. So if in this case, if the hydroxide is in excess, and then both of the two H plus from the carbonic acid will be consumed. So this is why the major product is carbonate in the first case. Does this make sense to you? Okay, good. The number 7, our goal is to convert sodium hydroxide into sodium carbonate. How we achieve this? We use sodium hydroxide. Oh, sorry, it's the opposite. We use sodium carbonate to react with calcium hydroxide. And because the calcium carbonate is a precipitate, and we got the byproduct, which is the sodium hydroxide. But if you change this into another ionic equation, the product actually is the spectators. So it's gone from the equation, right? But actually it is the product here. And the driving force is the precipitation. So this reaction is a little bit weird. I think now probably it will make more sense to you for the reaction number 9, right? It is also an acid-base neutralization. This is the diprotic acid, which is the acid. This is the base. So the acid donate or transfer a H plus to the base. And then the base change into bicarbonate. At the same time, the acid also change into the bicarbonate, right? So this is why the only product is bicarbonate, right? Are there any further reactions you want me to talk about? Okay, great. So let's move forward. The next one, alumina. Alumina is very important because it's amphoteric. When we say amphoteric, it means it can both react with acid and base, right? So I think it's easy to understand. A metal can react with an acid, but it's somehow a little bit weird, for a metal to react with a base, right? And in the basic condition, a complex is formed, aluminate. So let me try. How about those reactions here? Let me also, briefly talk about some of them. For example, if we want to convert aluminum into aluminum chloride, we can either make aluminum reacting with a chlorine gas, right? Basically burn the aluminum in the chlorine gas. We can also, react aluminum with the hydrochloric acid, because aluminum is a pre-hydrogen metal, so it will produce hydrogen gas, right? So we have two different methods. Number 3 is the most important reaction here. It is the evidence to support aluminum is a amphoteric metal because it can react with the base. So it forms a complex called aluminate. So I want to ask you guys, what is the byproduct here based on your understanding about the redox principles? Any idea? How about oxygen gas?
Water?
How about water? Any different opinion? So now I think this is a great example to test your understanding about redox principle. Please analyze which element is oxidized, which element is reduced. Okay, aluminum definitely is oxidized. So do we need to have an element to be reduced? So we must have an element to be reduced, right? So if we produce oxygen gas, is the oxygen reduced or oxidized? The oxygen here in water or hydroxide are -2. If you change it into O2, actually it's oxidized. So you have both two elements oxidized and no element to be reduced. That is the problem, right? So I don't think it should be oxygen gas. If it is water, maybe, but we didn't find the element to be reduced yet, right? So if you go through all of the elements in the system, which is the only possibility to be reduced? Yes, it is the hydrogen, because only hydrogen is +1 here, and it can be reduced. It has the potential to be reduced. So it forces you to write down hydrogen gas, although in the beginning, you probably is not very sure, right? So this is the power, of the redox principle. This is also the goal I want to, ask you guys to master after the class today. Maybe there is water in, not very sure in which side, more likely to be in the left side, because it seems like the left side need to have more hydrogen, right? Oh, by the way, in the USNSO National Part 2, although you are not supposed to balance the reaction, but you need to realize we need to add water in one side for some of the reactions and need to figure out which side needed. So somehow it's not need to have the full balance, but you probably need to check which side probably need to have the water. So I think this is a very good reaction. So if you compare this with this reaction, now it demonstrates aluminum is amphoteric. Oh, not really. The problem might not give you all of the products sometimes. I think for most years, it does not give you the products. Am I right, William? For the question number 5, number 6, reaction writing?
I think so.
Yeah. So you need to figure out what are the products. The reactants definitely would be provided, but if water need to be involved in the reaction, it will not emphasize, please include the water in the reactants. No, definitely not in this way. So you need to figure out by yourself. Let me see. I think the other reactions are relatively straightforward. I want to briefly talk about this reaction. Most of the weak bases are easy to decompose into water and either the oxide or the other stuff. For example, ammonia hydroxide, weak base, right? It decomposes into ammonia and the water. And like iron 3 hydroxide, easy to decompose into iron 3 plus, iron 3 oxide and water. So you can write down a lot of reactions like this way. This one need to be heated. This one can be done at room temperature or T. Do you guys have any question about number 9 and number 10? Why I emphasize these two must be in excess? Think about if this one is in excess, what will be the problem? Based on this reaction, number 6 and number 7, the excess hydroxide will further react with aluminum hydroxide and dissolve the precipitate, right? This is the problem. So some of the precipitate will be converted into the complex, the aluminate. So similarly here, if there is excess H+, the aluminum hydroxide will also be partially dissolved, right? And if you don't want to, dissolve the products, you can use weak bases or weak acids. For example, here, you can replace the hydroxide by using ammonia. Ammonia. I think we probably need to have water in the left side, right? In this way, because ammonia is not basic enough to further dissolve the aluminum hydroxide. And in the number 10, you can also use the weak acid because weak acid is not strong enough to dissolve the aluminum hydroxide. Okay, are there any other reactions you want me to go over? Okay, cool. Next one, iron, representative for transition metals with multiple oxidation numbers. Okay, let's go over these reactions. I want to briefly talk about the first one. When the iron wire is burned in pure oxygen gas, it will react very rigorously and produce a black solid. I can show you the video here. This is the burning. Probably it cannot be called rusting. Can you hear the background music? Okay, good. I don't like the music. It's too loud. I can share the sound with you. Okay, I think you see, the rigorous burning, and you probably see, there is a layer of water in the bottom, which is used to protect the bottle. Otherwise, the very hot, the red hot products. Can you guys still hear me? Great. My earphone is running out of battery. So the water is used to protect the bottle because the product is very hot. When it put on the glassware, it might. Okay, so the product here is iron 3. No, I even don't know how to call that. Maybe we can just say Fe3O4. But this is a pretty complicated oxide. You might know this is the magnetic iron oxide. Another reaction is regarding the comparison between the hydroxide reacting with iron 2+ and iron 3+. Let's also have a quick look. So in the left side, there is iron 2+ solution. In the right side, the iron 3+ solution. But I think the color is a little bit weird because the iron 3+ is supposed to be yellow. So now you see the difference, right? In the left side, is the product is the iron 2 hydroxide. It's supposed to be a white precipitate, but it quickly oxidized and slowly quickly changed into green and then slowly changed into reddish brown, which is the color in the right side. The reddish brown precipitate is iron 3 hydroxide. So I think these two reactions are easy to understand, right? Iron 2+ reacting with hydroxide produce a precipitate. Iron 3+ reacting with hydroxide produce another precipitate. But the color, this one is green. Actually, it's white, but you can only see green since there is always dissolved oxygen in the water. So it quickly oxidizes. And this one is reddish brown. So we can also convert the iron 2 hydroxide, with air into the iron 3 hydroxide. Let me quickly find the video, which is here. I think we can skip some. Okay, this light green solution, I believe, is iron 2+. And then sodium hydroxide is added. And the subtitle is wrong. It's not, iron hydroxide. It's sodium hydroxide. A dirty green precipitate start forming, and then you will see the color gets darker. And then if we let the solution stay for a while, it continue, to get even darker. And if we swirl the test tube for a relatively long time, or just leave it there for a long time, it changes into this color, which is quite similar to the iron 3 hydroxide.
So you can see, the reaction is in between the dissolved oxygen in the water or the oxygen from the air and change into the ion 3 hydroxide. The last two reactions are here is how the ion 2 plus, is converted into ion 3 plus and vice versa. So you need to add a strong oxidizing agent to convert ion 2 plus into ion 3 plus. Obviously, you need to add a reducing agent to change the ion 3 plus into ion 2 plus. So the best reducing agent is iron itself, as we discussed in the previous part, right? So now I think I will give you a homework. You guys can take some time to try to summarize something called aluminum triangle and iron triangle. Aluminum triangle is non-redox reaction because it's mainly about the three forms of ion 3. Ion 3 plus, ion 3 hydroxide, and aluminate. Aluminum 3 plus, aluminum hydroxide, and aluminate. So there are 6 reactions to make this triangle, right? All of those reactions are redox, but you definitely can make it more complicated. For example, you can start from the aluminum here and then change the aluminum here. You can also try to think about how to change it back. And here you can also think about how to convert the aluminum 3 plus into aluminum oxide. And there's one more reaction I want to briefly discuss. Leave as your homework is about this reaction. Think about why these two can react with each other to produce the aluminum hydroxide. You can take some notes first and leave this as your homework to further think about. And for the iron one, it is the redox triangle. There are probably also 6 reactions you can figure out, right? Not all of the reactions can easily, found, but you can definitely think about how you can make the conversion. Okay. Any other reactions listed here? You need to have a further discussion. Great. And then the next part is about the single displacement and the non-metal reactivity. So I think the most typical example is the halogen halide displacement, right? I think maybe we can have a quick look about this video. I think it's good for you to know the color change. Oh, what are those stuff? This is the bromine water. Oh, sorry, I missed some parts. Okay, now I understand. Let me take some notes. If I didn't understand wrong, I think this one is the chloride, this one is the bromide, this one is the iodide. So this whole column, 1, 2, 3, are all chloride. This 1, 2, 3 here are all bromide. This 1, 2, 3 here are all iodide. And now we are going to add, the chlorine water, the bromine water, and the iodine water into each, flask. So we add the iodine water to each of them, and we will see, there is no color change because the iodine water is kind of, has a color like this. So this is just the color of the iodine water. And then later on this row, we are going to add the bromine water. On this row, we are going to add the chlorine water. And then we will see. So this is kind of a now finally it's good. And then let's go. But my stuff is not in the right place anymore. So now I think the key part is coming. So bromine water is added to iodide. Did you see that? So the product has a darker color than the bromine water itself, which means iodine is produced here, right? And then if you go to the first line, when the chlorine water is added, I think now you can see it clearly. When the chlorine water is added to the chloride, there's no color change. But when it's added to the bromine, it produces the Br2 because the color is getting darker. When they add the iodide, it changes into I2. So basically, based on this 9, experiment, we can conclude the chlorine is stronger than bromine, is stronger than iodine as oxidizing agent. Or you can say iodide is stronger than Br minus, stronger than chlorine minus as a reducing agent, right? So I think this makes sense, right? Guys, we don't have much time, to show you the full video. So make sure, you watch the video by yourself if you have any question. So I think we already discussed why the reactivity of the halogens decreased down the group. We also discussed, what is the reaction when the fluorine gas is bubbled into water. So now I have another reaction for you guys to think about. Oxygen gas is bubbled into the H2S solution. Any idea here? Let's try. I think SO2 and water is a good gas, but I think it's more likely to be sulfur and water, right? Because sulfur cannot be oxidized by oxygen gas in the aqueous solution. You need to burn the sulfur. So the sulfur will be a more stable product in this case, but I think the ideal direction is pretty good. Does this make sense to you? So this is actually the precipitate. Okay, cool. So in the last part of the class today, I want to briefly talk about 2 typical redox titrations. And actually, we already had some good discussion before, right? The first one is called Permanganate Trometry. This is really a long name, but the idea is just use the permanganate to do the titration, right? I think this is the magic of English. It can make the word very long by adding the prefix, the suffix, and then show something meaningful. Okay, the genre I think is very clear, but what we want to discuss here is about this table. Hey, where's my table? Right here. It's about this table. So the permanganate actually is a strong oxidizing agent, but under different media, it can get different products. For example, in very acidic, the permanganate will be reduced, turned into Mn2+. So as you can see, you gain 5 electrons, right? We change from +7 to +2. And then you definitely can balance the reaction by yourself. We need to add water in the right side for water, so we need to add 5H+. You can check the charge in both sides to confirm whether it's correct or not, right? So this is the most typical, reaction for the permanganate. So this is also why when we do the titration by using permanganate, we always acidify the solution. And the Mn2+ is colorless. It has a very large positive standard reduction potential. This is good. Everything is good, right? It is strong, it's powerful, and the product is colorless, which means the color of the products won't affect the titration. This is also why we don't need to add any external indicator. We just need to use the purple color of the permanganate to do the titration. right? Very good. If it's on the near neutral, actually, it will change into a brown precipitate. Can you have a guess about what might be the precipitate here? MnO2? I would say MnO2 is a good guess. It can be brown or black, because if you use MnO2 before, probably you will see it's black. But the color, of the precipitate in the solution might be slightly different from, the powder. So this time, it will gain 3 electrons. And we also need to add H plus in the system, or otherwise we need to add hydroxide in the right side, since it's near neutral. So it's more reasonable for us to add the hydroxide in the right side. How many hydroxide? I think it's 4. So we need to add 2 water in the left side, and then we check. I think now it's good. It's balanced. So this is a precipitate, MnO2. So this is also why we want to acidify the solution. If you don't acidify the solution, there will be a side reaction like this, right? To produce the MnO2 as a precipitate. This is something we don't want to have, because it will affect your observation to the end point, right? The last one, if it's in very basic solution, it will produce a green solution. The MnO4 minus will gain 1 electron, change into the manganate. The manganate. This is green. Oh, but that's it. We're good. It is balanced. Unbelievable. It just gained 1 electron, right? So the last one, as you can see, is not very strong. The standard reduction potential is getting much smaller. So I think now, we already answered these 2 questions. So for this method, we can use it to oxidize a lot of products, such as iron 2+, change into iron 3+, Mn2+ into MnO2. Yeah, I think so. Oxalate into carbon dioxide. How about this one? What will be the products of the nitrite? If it's oxidized by the permanganate, should be nitrate, right? Because nitrogen is supposed to have +3 and +5. Nitrite into nitrate. H2O2 turned into oxygen gas, right? Okay. The next part is very useful about the Probate diagram. What is the Probate diagram? Basically, it's the EPH diagram. So it's how the reduction potential is changing with the pH of the solution. So the E here is kind of the E standard prime. What does it mean? So which means except the H plus, all of the other species are in standard states or in 1 molar. But the H plus cannot be always 1 mole per liter, because this is a function in between the E and the pH. So I want to emphasize this E is not a random potential, it's the E standard prime. So the only exception, which is now 1 molar, is the H plus. So based on this diagram for manganese, I think you can find a lot of useful information. The first one, what are the 2 dashed lines here? Did you see that? Now check the E value at standard states. When the pH is 0, which means the H plus is 1 molar, and then we go up, we got this point, it's 0. We go up, it's around 1.2 something, right? To cross this 2 dashed line. So now can you figure out what is the bottom dashed line? the E standard is 0 volts. So this line actually is the E standard prime of the H plus hydrogen gas. Make sense? And you guys can use the Nernst equation to derive the equation of this dashed line. You will see the equation is like this. Is minus or plus? I think it's minus, right? 0.0591 over N log H plus. Now I think it's plus. Yeah, take some time to derive it by yourself. This is not, it's off topic today. So you guys can do some further discussion by yourself. So if you change this into pH, it's changed into E plus minus 0.0591 over N pH. So basically, I want to say the slope of this dashed line is supposed to be negative 0.0591. This is, the results based on the Nernst equation. How about this one? This one actually is the oxygen water. Oxygen water. If we are clear about this question, I think now we can further answer a few more. So why are some lines vertical? For example, here. Why are some horizontal? Let me see here. Why are some, slash? Let's first emphasize these two. What are the characters of the, vertical lines? You can check the two species, in both sides, right? In this side is Mn2 plus, in this side is MnOH2. And here is MnOH3 minus. Can we say they are non-redox reactions? Right? So this is why under the same pH, there is no, how to explain? It's kind of hard to explain, but I think we can get a feel, right? It's a non-redox reaction, then it's vertical in the Probate diagram. How about those horizontal lines? There's only one horizontal line here. Horizontal means the E standard, the E potential, the E does not change with pH, right? For example, here. So I think we can say this is a half reaction, is a redox half reaction, but there's no H plus or hydroxide involved in the half reaction, right? For example, here is Mn2 plus gain 2 electron, change into Mn. So the pH won't affect the E potential, right? Okay. My next question is, why there are some slash? Obviously, they are E potential. Their E will be affected by the pH, right? Some of them have different slope. For example, here, you guys can take some time by using, the Nernst equation to figure out why they have different slopes. Although a lot of them have the same slope with the hydrogen and the oxygen lines, right? Okay. What happens if manganate, where is manganate? Manganate is in this small triangle. So this is why it's only stable when the pH is very high, about 13 to 16. Basically, it's very basic solution. The manganate is stable. If the solution is acidified, what will be the reaction? Let me, erase some of the contents here for you to have a clear idea. it will disproportionate, change into the permanganate and MnO2. Does this make sense to you? Well, if we shift the pH to the left side, and then you will see the two neighboring species are the permanganate and the MnO2, right? And we can further, confirm by using the standard reduction potential here. So let's say if it's proportionate into this and this, now let's check. This is the cathode, right? Reduced. This is the anode, oxidized. So we just need to confirm that cathode has a more positive standard reduction potential than the anode, right? It seems like we need to do some calculation because this one is good, but we don't know this one yet, right? So we may need to use, the values here to do the calculation. Leave this as your homework. Let's double check. Oh, there's another question. So we see the permanganate actually, the stable area, which is here. Did you see that? This area is above the dash line of the oxygen water line, right? The dash line, which means the permanganate can oxidize water and convert water into oxygen gas, right? Because it is above that line, which means it is a strong oxidizing agent. But we still have the permanganate solution, relatively stable, right? So there's a reason, because this line actually is the thermodynamic line, is a theoretical line. But actually, we need to consider the kinetics. The permanganates can oxidize water, change into MnO2 and oxygen gas. This reaction actually is spontaneous at room temperature. But the speed is not that fast. So this is why we don't need to worry too much. But if you leave the potassium permanganate solution for a long time, you will see in the bottom of the bottle, there will be some black precipitate produced. So this is one of the reasons why permanganate always need to be standardized, because the concentration is not fixed. It might change with time. I think we already answered this question, why the permanganate solution needs to be acidified in titration. We want to see a clear color change at the end point. So once it's acidified, the product is Mn2+, right? Or a very important reaction here. What is the reaction when MnO2 is heated with concentrated hydrochloric acid? Can you guys have a guess? First, I want to tell you it definitely is a redox reaction. MnO2. So Mn is reduced. So what will be the element to be oxidized? Okay, so we will say the product is MnO2, react HCl, produce Mn2+ plus Cl gas. Do you agree with this? So actually, this is one of the reaction in the National 2018 Part 2 5D. So this is also the most common used method to produce chlorine gas in the chemistry lab, because this reaction is controllable, is relatively slow. Because if the reaction is too rigorous, you cannot even safely run the reaction and collect the gas, right? Okay. Another method to make chlorine gas can be found in the video. Basically, you mix hydrochloric acid with bleach. Do you guys know what is the major component in the bleach? it is the hypochlorite. Hypochlorite, the chlorine is +1, but actually it is a pretty strong oxidizing agent. So when it meets with the hydrochloric acid, it will proportionate change into hydrogen gas and water. So this is a quite similar reaction. So as you know, both the bleach and hydrochloric acid are used in the kitchen. They are household products, right? But mixed then are very dangerous because chlorine gas is toxic, right? So you cannot misuse these two at the same time. Yeah, I think we can have a quick look. As you can see, a lot of bubbles are produced, but right now, you cannot see the color of the bubbles yet. Oh, no, this is not right. This is not right. What this? Oh yeah, this is kind of a solid bleach, right? If you dissolve the solid in water, you get the bleach because it's the calcium hypochlorite. And then if you add the hydrochloric acid, as you can see, bubbles produced. The bubbles are light green or yellowish, something like that. That is chlorine gas, right? That chlorine gas. Oh, there are some other stuff. So this is the way, but we don't use this method in the chemistry lab to make chlorine gas because the reaction is too fast, it's too rigorous. I think, how about we finish the last question and end the class today? We have some contents remain in the handout regarding the iodometry. I think we probably can continue our discussion in the beginning of the next class. The next class probably will be shorter because non-redox reactions actually are easier to understand compared to the redox reactions. We probably will take another 30 minutes to finish this one. Okay. Let's finish this last question. How to calculate KSP of MnOH2 based on the Probate diagram? This is pretty interesting, right? How is this related to the KSP? Nernst equation. KSP equals to Mn2 plus times hydroxide to the power of 2, right? Hydroxide definitely is related to pH. This is a very good point. So which line you want to focus on? Because you must analyze the lines here, right? So I think you definitely need to focus on this line, right? Because this line is in between the Mn2 plus and the MnOH2. So what is the meaning of the intercept on the x-axis? This pH shows the molarity of hydroxide, right? So if we know the molarity of the Mn2 plus at this moment, we can calculate the KSP, right? Do we know the Mn2 plus at this point? Yes, we do, right? What that? Please keep in mind. they are all E standard prime, which means except the H plus, all of the other species are in standard states, which means the Mn2 plus is 1 molar, right? So we can say the Ksp equals to 1 molar times about the pH is about 7.5. So the pOH is 6.5. So it's 10 to the power of negative 6.5 squared. And we got 10 to negative 13. That is a kind of estimate of the Ksp. Because, you know, we do not have too many significant figures. So we probably can get only one significant figure in the products, in the results, right? Okay. Oh, there's one more thing I want to say. If you compare these two standard reduction potential, you probably will realize, is MnO2 strong enough to oxidize the chloride? It's not, right? It's not. So this is why we emphasize concentrated, you know, HCl. What's the benefit to use the concentrated HCl? From one perspective, it will increase this value. Now, this makes sense to you? If we use the Nernst equation, E equals to E standard minus RT over NF ln Q. Am I right? And then you will see the H plus actually is in the bottom of the line. So a higher H plus will decrease the Q and increase the E, right? Or you can just use Le Chatelet principle. More H plus will shift the reaction to the right side. So this is why H plus is good to increase the oxidizing ability of MnO2, which is good for the reaction. And secondly, a larger concentration of chloride will reduce this molarity, right? Well, think about chlorine gain 2 electrons, change into chloride. So if you have more chloride, the reaction is easier to shift it to the left side, right? If we just use LCP to have a qualitative analysis, you got the results. So it's working in two different perspectives, which will make the reaction ongoing in the side we want. Okay, let me see. May I, assign this challenging question as your homework? I believe you probably need to take some time to go over the packet after class and try to go over the reactions as well. I think the class, from my perspective, is pretty informative today, right? You definitely need to take some time to further digest the contents. I think all of my lecture notes are quite similar like this. It is packed with a lot of contents. So in general, I think the class, the pace will be relatively fast. So we don't have too much time for you to, to do probably a very thorough analysis in the class. So this is why I ask you guys to do some homework after class. And please also let me know if you have any suggestion to me. Let's say it's too fast or it's too slow, or you have any other, comments. So we will, talk about the remaining contents in the beginning of the next class. If we cannot finish, the contents, I will, make into a video and, a recorded video and, share with you guys. It seems like it happens so many times in my class. I always, try to put a lot of contents in the lecture notes. I think the pressure is not too high because I think there are not, yeah, you definitely can, go over the contents by yourself before the class. What is the time of our next class? Hey. Oh, I realized there's an issue in my website. So I have some new contents uploaded, but when you refresh it, it cannot be shown. Did you guys, see similar issues? No? Yeah, you see, I cannot show anything here. I probably need to change another browser. Do I have the Chrome? Chrome. This one. So the next class is actually on Tuesday. And the reason I didn't, actually I have a whole week of break, but the reason why I didn't, put the class on Monday is I think you guys probably need to take some time to digest the contents, take a small break, do some homework. But as you can see, the next few classes are very, are kind of connected. April the 1st, April the 2nd. Yes, yeah. And hopefully you guys can get the results back from ACS on April the 4th. This is the planned date offered by ACS. And then at that time, we'll have a better, idea about, how we can, keep going, right? Okay, great. Yeah, we took some time in the beginning of the class to discuss some, general information about class, my expectation, and what is the class for. So we extended a little bit